Welcome, everybody. I'm Djorgovski. I'm professor and executive officer for astronomy and director of Center for Data-Driven Discovery and one of the triumvirate of the organizers. One other thing about logistics is the demos are in the library just before you get onto the patio. And some of them may be even working during coffee breaks. It's not just at the end of the day, which is the official demo time. So I'll yield to Emily and Scott.
Good morning, everybody. Welcome. It was really nice to see a full house here, to have all of you here today with us. So I'm Emily Law, serving as the Deputy Program Manager for Data Science and Data System, as well as Technologies at JPL. We have a wonderful, great lineup, a very impressive lineup of fabulous speakers and presentations. So I'm sure that we're going to have a fun day. Enjoy your event today. Thanks.
Good morning, everybody. So my name is Scott Davidoff, and I manage human-centered design at the Jet Propulsion Laboratory. And I just wanted to say I'm very excited about the program we've been able to put together today, because it really represents, I think, such an interesting juxtaposition of disciplines. And I think this is really one of the essential kind of exciting opportunities about doing work in this area, because it really represents this really interesting fusion of ability to solve problems with new kinds of interactive computational graphics and the kind of really rich, complicated topic of space exploration. So I also just wanted to say thank you so very much to all the speakers who journeyed from far away to come to this event today and to share all of their interesting experiences and deep technical knowledge. So without further ado, why don't we jump in and get started? I think, Emily, you're going to chair the first session.
Thanks, Scott. Again, thank you for coming here. Really nice to have you all, and it's really an honor to have this opportunity to organize this event with our esteemed colleague, Michelle, Scott, and also George. So let the fun begin, and our first speaker is going to be George, and he's going to be talking about VR and AR as a scientific and education platform. So let's welcome George.
Thank you. Well, thank you, Emily. Thank you, everybody. So I'm the warm-up band before the real show. And so I'd like to tell you in very broad terms, why are we here, why I think we're here, and how did I get to be here? So many people, myself included, think that we're now transitioning to the new step in the evolution of the way we interact with computers. We started with mainframes, went through desktops and laptops and mobile, and now we're moving into the era of augmented and immersive virtual reality or mixed reality, which I think will all blend into seamless fashion. So as you look through this technological evolution, you see many trends, not just compute power, but usability, fidelity of what's been presented to a human, total information content, the rate of the content, diversity, immediacy by which you can see it, and that trend will likely continue. There's something comes after the web and the internet, and the interesting question is why? So another important thing which really touches upon the whole idea of data-driven computing is that most of the time we use computers not to compute anything. We use them to discover and access and process information of different kinds. So interesting question is, where does knowledge come from? Where do ideas and discoveries come from? And I think basically a lot of it originates on interfaces. Interfaces of human minds with each other, discussing, crystallizing things, human minds and information content, whether it's text or data or abstract concepts. This is where new things happen. Also, the interfaces of different fields increasingly, and computation plays the role that mathematics and statistics played in the past of serving as the universal language to enable interesting multidisciplinary, transdisciplinary studies. So any new technology that helps or facilitates these interactions on interfaces is a good thing. And I think we're about to get into the best one so far. for me, this started about 10 years ago with a group of astrophysics friends and others. We conducted an experiment with the early days of virtual reality with virtual worlds as a platform. And the question was, what can this technology do for us as scientists or educators, as scholars? It's good for things other than blowing up spaceships. And we conducted NSF-funded project called Meta Institute for Computational Astrophysics, which was the first, and I think so far the only, professional scientific organization that was based in virtual worlds. So we did play with it, and we tried several things involving human interactions like collaboration meetings and seminars and classroom lectures and public outreach lectures, but also started playing with data visualization, which would be one of the main themes here. So even though technology was fairly primitive then, we saw immediately it has a huge potential. And now I think this is finally coming to blossom and people are beginning to realize this is the case. If you're curious, a brief report of what we've done is in that paper on the archive. So things that we've done first involved human interaction. You can see this is pretty cheesy graphics, but that's what you had back then. And so we had proper seminars and collaborations and public lectures, including by Nobel laureate occasionally. And we found out that even back then, this technology was already a killer app for anything involving human interaction. And it cost nothing. So you can do a very effective worldwide telepresence, way better than Skype or any form of video conferencing, no cost. And don't have to travel, right? We can organize conferences like this one at zero cost. So this is why we organize conferences in nice places like Southern California in the winter, so people have an excuse to travel, right? But to me, the more interesting part really was tackling the issue of multidimensional data visualization. I've been playing with what's now called data science for quite some time now, and very early on, I realized that the big problem that we have, which I think is still the key bottleneck of all data science, is the ability to visualize effectively high dimensionality data spaces. Because it's not just the data size, in fact, that's the least important part, it's the data complexity and informational content. In many cases, data can be represented as feature spaces with tens, hundreds, thousands of dimensions. And how do you actually see what's going on there? So it turned out that virtual reality provided a better way to do this, better than any traditional flat screen graphics. And even though if you interact with a flat screen, the subjective sense of immersion really made a difference. The scientists can walk into their data, interact with their data, interact with their colleagues, and colleagues can be on the other side of the world. And somehow being inside the data looking out was way more intuitive than being outside the data looking in, which is the traditional approach. So this will be a theme that will come again and again, I think, in this meeting. Well, what did we learn? Well, first, we learned that this is just unreasonably effective for anything involving people, that we're evolutionarily optimized to deal with information and other people and objects in a 3D world. And so this was like the first taste of actually being able to do this through a computer interface. There is an interesting phenomenon. There are many, many studies why this works the way it works. And it's called Proteus effect, that people identify with their own digital representations online, and somehow these interactions in immersive VR are classified in your mind in the same way as interactions in the real world, very different from interactions you have on the phone or Skype or email. And even though technology was pretty poor by present-day standards, minds can interpolate over it, just like your vision interpolates over the scene easily. Well, turns out we were pretty much on the bleeding edge then, and we did bleed. There was a very slow uptake by the academic community. People just did not like it. They just had idea this was not something not serious, video games and so on. Partly well justified, but the times have changed now. VR and AR are clearly becoming mainstream, and furthermore, workforce of today and tomorrow are digital natives, and for them there is nothing more natural than interacting in some form of virtual reality. And if you have young children, then you know about Minecraft and things like that. So let me focus now on the issue of visualization. I think this is really a core issue of data science, and that you cannot really understand something unless you can visualize it. Even mathematical concepts, you have to visualize in some form or other. So when what you're looking at is simple, no problem. But now we're dealing with increasingly more complex phenomena, and this becomes a real barrier to our understanding of what's hidden in our data. Now, this is a problem, because as I mentioned, modern data spaces can have tens, hundreds, thousands of dimensions, and we're sure there is interesting knowledge hidden in those many dimensions, but how do we find out? And it's a two-stage process. First, you have to look at your data in order to decide what are the appropriate algorithms that you use to analyze them, because just like they say about data garbage in, garbage out, if you're using wrong algorithm, the same thing applies. Garbage algorithm, garbage out. And this is a problem, because we deal with 3D world. It turns out that with different tricks, you can see up to maybe a dozen dimensions. Most people can saturate at about 8 or so. And so what good are these data if we can't extract knowledge from them? So this is why this is a crucial thing, and every little thing that can help you go one step further, add an extra dimension or two to what you can see, wins. The state of data visualization is really dismal, at least for most people. Typically, they look at one-dimensional displays, histograms, and so on, maybe scatter plots and so on. Every time you down project high dimensionality structure to some lower dimensionality, like flat XY plot, you smear and lose information. So you definitely don't want to do this if you can help it. This is really where VR comes in. This is video of a just desktop version, but basically, once you can plunge into data, you get a much more intuitive sense of the data geometry, possible outliers, you can query the data. Here we have a 6-dimensional data space of actual astrophysical data with X, Y, Z positions, shapes and colors and sizes, and it's way more effective than any traditional set of 2-dimensional plots. The next thing I would say we should think about is that this is actually probably the optimal way so far for interaction of carbon-based brains and silicon-based brains. That somehow interacting with machine intelligence, with machine learning algorithms, analysis, comes more naturally in one of these abstract immersive data spaces, because somehow you're prepped for that. And since we're going to be increasingly using machine learning, machine intelligence in analyzing the data, because we need some sort of augmentation of what we can do with our own brains, a platform that makes that easier will be a very important thing. I predict that before too long, this is how everybody will be analyzing their data, and you'll just never want to go back. You know, forget Excel. Sorry, Microsoft. And in fact, there is an example as a spin-off company from Caltech and JPL that will be represented here and discussed later in the day, and there will be a demo. So I invite you to go and check it out to see how this actually works in practice. So to conclude, I think we're in a very important junction that the new technology of AR and VR is qualitatively superior to anything we had in the past to interact with computers, to interact with the data, and even to interact with each other over large distances. And more importantly, since artificial intelligence, machine intelligence, is playing increasingly large role, if you have a better, more natural, more intuitive way to interact with machine intelligence than, say, just a little box in Google or Bing, then this would be a very important thing. Instead of just talking to a speaker like Alexa or Cortana or Siri, you'd be interacting in some more intuitive representation of the machine that does your bidding. And in fact, we're moving towards collaborative human-computer discovery. So I would say that what's coming is transformation on par with what happened with the web, that everything was transformed. Every industry, every aspect of modern human life has been transformed by going onto the web, which we now see through two-dimensional interfaces. I think equally transformative will be what's coming, and who knows what's going to happen, but I'm sure that science, technology will be part of that. So with that, I'll stop. I'll be happy to take any questions. Yeah, and I'll repeat the question if there are any.
I can run it.
Okay.
We have about 5 minutes for questions.
Yeah, Deborah.
Yes, I was interested when you said Deborah, if you want to use the mic because we at least want to get the question. I was interested when you said that humans could possibly see up to 12 dimensions. Where do you get that?
You can actually encode as many as you want in a display. I mean, you always have X, Y, Z. You have colors and shades and transparencies and shapes, and you can put textures on data points. You can animate the data points, make them spin or pulsate or glow. You can sonificate the data. You can make data points sing different tunes to you. But at some point, you just can't keep track of it all. And in our experience, 6 is really easy. And most people can do 8 with just a little bit of practice. Experiments have been done, multiple experiments in different ways of visualizing the data that found out that saturation point for humans seems about 12 dimensions. Mm-hmm. Yeah.
So you mentioned that sort of interacting with the data in the kind of immersive virtual reality environment was sort of more intuitive for understanding the data. Do you have any examples, even just maybe anecdotal, where either a scientist or data scientist was looking at their data in, say, 3 dimensions or in an immersive environment and saw, I guess, some pattern that they didn't previously see?
Well, we see many such examples as we play with the data that you can. The VR enables you to bypass a lot of limitations of traditional 3D graphics because of perspective and occlusion and other effects. You just have to try it. It's not something that's easily explained, but sometimes it lets you see things that you cannot see otherwise because of the projection effects. But more often, it lets you find things faster than you would through any traditional visualization tool, which can make a big difference, especially if you're mixing visualization with machine learning.
About your initial studies back in 2008.
Oh,
yeah, go ahead.
I'm sorry, I just wanted to add one thing to George's answer for the previous question. I think if you actually stay for the remainder of the talks, you're going to hear quite a few different examples from the speakers where they're going to provide a number of different examples of applications that have been used to create insight in particular dimensions. And so Parker, who may not be here yet, is going to show a representation of virtual Mars, and will show studies that were done on virtual Mars where scientists were better able to understand the environment in a way that they were simply unable to do previously. Bashak is going to give a talk on trajectory design visualization using VR, and will show that there were a number of ways that the trajectory designers were able to understand the trajectory in ways that they simply weren't able to before. So actually, I feel like there are many, many examples, and the talks today will actually be focusing on them to make sure that you get a sense of the kind of broad range of problems. But I think what's very interesting is they often have a kind of core spatial component. And one of the questions that I think we'll wrestle with today, and I've been hearing, I'm seeing into the abstracts of the talks from our speakers, is that they're asking, is that necessarily the case? Is there also an abstract analysis that we can do that's non-spatial that we get advantage of in virtual reality? Or does that make things harder? But it's a very interesting question. Okay, sorry, George.
Thank you, Scott. So there was one more question back there.
Yeah, I just had a question about your earlier studies from the NSF funds, and I was just curious what takeaways did you take from the classroom experiences that you did in VR in those early days?
Well, any experience of interaction, whether it's professional seminars with PowerPoints, 2D PowerPoint in a 3D world, or public outreach lectures, or classroom instruction, everybody was reporting subjective sense of almost being there and interacting in a more natural way, remembering what was said and what was done. There is actually a very vibrant and forward-looking community of education professionals who have been experimenting with this technology for many years now, still do. They actually put most scientists to shame because they're really forward-looking and try to see what technology can do for education. And I think in particular, when it comes to online learning, I think there is great promise of doing things like virtual labs that are not based on physical location, or even making labs that are simply impossible to do in physical space. All right, thank you. Yeah.